I was looking at my phone this morning, just staring at it while it charged. And I had this certain thought, of how wildly improbable it is that this thing actually works.
Ideally, yeah. That's the hope.
I mean, think about it. You buy a phone or a car with 1,000 sensors or, I don't know, a medical device. You take it out of the box, you hit power, and it just works.
That's the baseline expectation.
But the sheer number of electrical connections inside, it's just staggering. We're talking thousands, maybe millions of little contact points. And if just one of those solder joints is cold or one chip is seated wrong, the whole thing is just a paperweight. So how do they actually know?
Right.
They can't possibly have a human sitting there soldering wires on and off every single chip to check it.
No, that would be completely destructive. You can't solder and unsolder components just to test them. I mean, the heat alone would just ruin the board.
So what do?
You need what we call an invisible test.
An invisible test.
You need a way to establish a perfect electrical connection, check the signal, and then just vanish without a trace. And that is where today's topic comes in. We are doing a deep dive into the unsung hero of the electronics world, the spring probe.
It's funny because when I first saw that term spring probe, I pictured, a spring, just a little coil of wire.
Yeah.
But looking at the engineering specs you sent over, that is a massive understatement.
Yeah.
This is not hardware store stuff.
Not at all. It's a high-precision electromechanical instrument. Think of it as a bridge.
A bridge.
On one side, you have the device under test, your new smartphone motherboard, and on the other, you have the massive, expensive test equipment. The probe is the critical link that connects them.
And it has to do it fast, right?
In milliseconds. It has to carry power and high-speed data, often in environments that aren't perfectly clean, and then release instantly so the next unit can slide in.
Okay, so our mission today is to figure out how these tiny mechanical marvels essentially hold the modern world together, from the famous bed of nails to the connectors inside the devices themselves.
It's a fascinating journey into the sub-millimeter engineering that makes all this reliability possible.
So let's start with the anatomy. If I were to put one of these under a microscope, because I assume they're tiny, what am I actually looking at?
Oh, they can be thinner than a needle, but the construction is incredibly consistent. It's a precision assembly of three main parts.
Okay, break it down for me.
First, you have the plunger. Sometimes they call it the pin.
Okay.
That's the active end that actually touches the device. That plunger sits inside a barrel or a tube, which is just the housing.
Got it.
And then tucked inside that barrel, pushing against the plunger, is the spring.
So plunger, tube, spring. Pretty simple mechanics, but I noticed the materials you listed are really specific. We're seeing a lot of brass, bronze, and copper.
Right. You need those copper alloys for the base material because they're excellent conductors, but the finish is where it really matters. You'll almost always see a thin layer of silver nickel and then, and this is crucial, gold plating.
Which makes total sense. I mean, gold is the standard for anything, where you need low contact resistance and corrosion protection, isn't it?
Exactly.
You can't have your test equipment rusting.
You can't. If your probe oxidizes, your resistance goes up, and you get a false failure. You end up throwing away a perfectly good phone because your test tool was dirty. Gold prevents that. It ensures the electricity flows with almost zero obstruction.
Okay, now there's a mechanical concept here that I want to unpack.
Yeah.
The working stroke. It sounds like something out of an engine manual.
It's actually more like your car's suspension.
Oh, okay.
You don't want your suspension fully compressed, bottoming out against the frame, but you also don't want it barely floating at the top. You need to be in that sweet spot.
So the probe needs to be compressed just the right amount.
Precisely. Every probe has what's called an initial spring force, just to get it moving, and a maximum spring force when it's fully squished. The working stroke is that middle ground, usually about 2/3 compressed.
And why there?
That guarantees you have enough pressure to sort of bite through any dust or oxide on the board, but not so much force that you actually puncture the circuit.
Ah, a Goldilocks zone for pressure.
Exactly. And hitting that zone is just critical when you have thousands of these things acting at once.
That brings me to the part of the research that really, really surprised me. I assumed the tip of the probe, the part that touches the phone or the chip, would just be a point.
Like a needle, yeah.
Yeah, exactly. But looking at the catalog, it's an absolute arsenal of different shapes.
Oh, the tip selection is an art form. It really comes down to this battle between connection and protection.
Right, because you have all these different surfaces. Some are clean and delicate, some are dirty and tough.
Exactly. If you're testing a gold-plated pad on a finished consumer device, you cannot scratch it. So what do you use?
You'd have to go for the gentle options, like the round tip or the flat tip.
Right. The round tip is the gentle giant. It's non-marring. It just touches the surface, gets the signal, and leaves zero trace.
And the flat tip?
It's similar, but it's great if you're hitting a solder bump or a rounded surface where, a point might just slide off.
But then you have the complete other end of the spectrum.
Yeah.
The I don't care about scratches, I just need a connection group.
The aggressive tips, yeah. You have to remember, in a factory setting, circuit boards are not always clean. They can have flux residue, oxidation, maybe layers of grime. A round tip would just sit on top of all that dirt and fail the test.
So you get through it. That's where things like the crown, chisel, and razor tips come in.
Yes. The crown tip looks exactly like it sounds, little sharp points facing up. It's designed to really bite into wire leads or pads. The chisel is like a little blade that can slide to wipe away corrosion. And the 90-degree razor...
That one sounds like a weapon.
It practically is. It's a specialized, super sharp tip designed specifically to pierce through heavy contamination or conformal coatings.
So it just punches through the grime.
It punches a hole through the grime to find the metal underneath. Yes.
I also saw some shapes that seemed more about geometry, like the cup tip and the waffle tip.
Those are problem solvers. The cup tip is concave. If you're testing a long pin that's sticking up, you don't want your probe sliding off the side.
Ah, so the cup catches it.
The cup catches the pin and centers it.
And the waffle, the name is great.
Think of a waffle iron pattern. It gives you multiple points of contact, so it's sort of the jack of all trades. If you're hitting a flat surface, the little ridges cut through dust. If you hit a pin, the pin can catch in the grooves. It's incredibly versatile.
It just highlights that testing isn't just pushing a button. It's a mechanical challenge.
It is. It's about mating two imperfect surfaces.
And doing it thousands of times simultaneously.
Exactly.
Which brings us to the bed of nails.
Yeah.
That term always sounds like some kind of medieval torture device. But in electronics, it's just a fixture, right?
It's a fixture that holds hundreds or thousands of these probes in a very specific pattern. When the production line moves, the board is pressed down onto this bed. Every single probe has to hit its target at the exact same moment.
And the density is just insane. I saw pitches as tight as 0.4 millimeter. That's the spacing between the centers of the probes.
Less than half a millimeter.
Huh.
Imagine trying to pack springs side by side that closely without them touching each other.
If they touch, it's a short circuit.
And the whole test is useless.
But here's the thing that gets me. If you're building millions of phones, there have to be manufacturing tolerances. Things wiggle. The board might be slightly warped. How do you hit a 0.4 millimeter target if the board is just a tiny bit off?
That is the genius of the spring probe. It enables what we call blind meat technology.
Meaning you connect without actually seeing it.
And without guiding it by hand.
Yeah.
The whole system is compliant. It's forgiving.
Oh, so?
Because the probe is a spring, it can absorb misalignment. If the board is slightly lower on one side, that's the z-axis, the springs on that side just compress a little more. If the target is slightly off-center on the x or y-axis, the tip shape, like that flat or waffle tip, ensures you still make contact.
Okay, that makes sense. There's also a mention of a wiping action. I'm assuming that's not someone coming in with a little cloth.
No, it's all mechanical. Some probe setups are designed to engage at a slight angle. So as the tip touches the pad, it slides or wipes across the metal surface, just a tiny, tiny bit.
Like striking a match.
Exactly, but on a microscopic scale. That little motion scrapes away any dust or oxide right at the moment of connection.
Wow.
It cleans its own contact point every single time it tests.
That is brilliant. It's a self-cleaning connector.
Yeah.
Now, I want to pivot to the high-tech side of this, because we're not just testing if a light bulb turns on, are we? We're pushing massive amounts of data through these things.
Oh, we are. The specs I saw show speeds up to 56 gigabytes per second and RF bandwidths up to 40 gigahertz.
Okay, so this is where my physics brain gets a little skeptical. A spring is a coil. And in electronics, a coil is basically an inductor, right?
Right.
It resists high-frequency signals. It acts like an antenna. How on earth do you push 40 gigahertz through a coil without the signal just turning into noise?
You have absolutely nailed the problem. If the electricity had to spiral through that spring wire, the inductance would kill the signal. It would be a total disaster for high-speed data.
So how do they get around the spring?
They use what are called advanced biasing techniques, and the most common one is the bias ball design.
Okay, walk me through that.
So inside the barrel, they place a tiny ball bearing beneath the plunger. Or sometimes the plunger itself is cut at an angle. The geometry is designed so that when the plunger is compressed, that angle or that ball forces the plunger sideways.
Oh, against the inner wall of the barrel.
Exactly. It wedges it right against the tube. It creates a solid, continuous metal path from the plunger tip directly to the barrel wall, completely bypassing the coiled spring.
So the spring is still providing the force.
But the electricity takes the shortcut.
Through the straight metal walls of the barrel.
Right. It effectively turns the probe into a solid wire for the signal while keeping the mechanical compliance of a spring. That's how you get 56 gigavolt stability, even when there's shock and vibration.
Speaking of shock and vibration, let's talk durability. These things are working hard. If I'm a factory manager, how often am I swapping these out?
They are surprisingly tough. We're looking at a lifespan ranging from maybe 20,000 cycles for the really aggressive sharp ones, up to 500,000 cycles for the standard types.
500,000 tests. That's really impressive for a tiny moving part.
It is. And remember, they aren't always in a clean room. These probes are designed for what they call high reliability multi-cycle applications in harsh environments.
I saw mentions of IP68 and MELE 810 standards.
Right. So imagine you're testing a sensor that's going to go on an oil rig or a component for a drone that flies in the jungle. The test equipment itself might be exposed to dust, water, or extreme temperatures.
So an IP68 rating means the probe is sealed against dust and water immersion.
Exactly. And MELE 810, that's the military standard for things like shock and vibration. These probes have to survive the same punishment as the devices they're testing.
That actually leads perfectly into the final piece of this puzzle, because up until now, we've been talking about testing, using the probe to check another device. But these things are also used as permanent connectors, right?
Yes, and this is a really growing trend. Because they're so small and so reliable, engineers are now putting them inside the final products.
Like for battery contacts.
Battery contacts are the most common use, yeah. Think about your cordless drill or a removable battery on a two-way radio. When you slide that battery in, you want a connection that is absolutely solid, but you also need to be able to rip it out instantly.
And a traditional plug-in socket would be too tight?
A traditional pin-in socket is a friction fit. It requires force to insert and remove. A spring probe just presses against a contact pad. It allows for that blind mating. You just slide the battery in and the springs compress.
Plus, I imagine the vibration tolerance is huge. If I'm using a power tool, that battery is shaking like crazy.
Exactly. If you had a rigid connector, that vibration might crack the solder joints or cause what's called fretting, these little micro movements that wear down the metal. But the spring probe is compliant. It sort of floats. If the battery vibrates, the spring just expands and contracts slightly, but the electrical connection never breaks.
It just absorbs the movement.
It does. And because they have such a low profile, some are compressed down to less than 2 millimeters, they're perfect for board-to-board connections in really tight spaces, like stacking circuit boards inside a smartwatch or a hearing aid.
It's amazing to think that something as simple as allow for a little wiggle room is actually the key to reliability.
That's really the core philosophy here. Rigidity fails, compliance survives.
So bringing it all back, we started with this idea of the invisible test.
We did.
And we've gone from what I thought was a simple coil of wire to a gold-plated, high-frequency, self-cleaning data bridge that uses bias balls to cheat physics.
It's a lot of engineering packed into a space smaller than a grain of rice.
It really changes how you look at your devices. When you pick up your phone and it just works, it's not magic. It's because an army of these tiny little springs vetted every single pathway.
And it's a reminder that reliability is an engineering choice. As our devices get smaller and faster, that bed of nails has to get denser and smarter. We're really reaching physical limits where we are relying on these microscopic mechanisms to ensure the safety of our cars, our medical tech, our communications.
It's all hanging on the tip of a spring.
Hopefully the right tip.
Hopefully not a round tip on a dirty wire.
Exactly.
Well, I am definitely going to appreciate my battery charger a little more today. Thanks for breaking all this down.
It's always a pleasure.
And thanks to everyone listening. Keep looking for the invisible engineering around you, and we'll catch you on the next deep dive.